Hello, I'm Eren Mehmet Kral, and I'm going to present our submission, which has been accepted to AISTATS 2023. This is joint work with Thomas Mullenhoff and Mohamed Imtiaz Khan, who are both from Riken AIP, the approximate Bayesian inference team, with Imtiaz Khan being the team leader. I myself am also from Riken AIP, but I'm associated with the mathematical science team. And our work is the Lie-Group Bayesian Learning Rule. The Bayesian setting learns a distribution over the parameters of a machine learning model as opposed to a single parameter value, and it incorporates the Bayesian notion of updating a prior belief with incoming new data. It has benefits of uncertainty quantification, robustness, reduced overconfidence, and due to the updating of one's priors that I just mentioned, is a promising direction to search for continual learning. But also, the Bayesian setting is rich in mathematical structures, and as a theory, I think is at a sweet middle ground of flexibility and structuredness. These structures, the railing provided by these structures, can guide us in algorithm design, as opposed to coming up with a new variant of SGD, which is driven mostly by intuition and heuristics. That is too free in a sense. Our work is an extension of Khan and Ru's Bayesian Learning Rule, BLR for short. It has been successful and given rise to many a competitive algorithm and data analysis tools. As its name suggests, it is a Bayesian method, but has also yielded, upon specializations and approximations, a wide range of Bayesian and non-Bayesian learning algorithms, such as our beloved workhorse SGD, Newton's method, RMS prop, Laplace's method, among many others. And members of the approximate Bayesian inference team have already developed new and successful methods using BLR, such as the Vaughan, the Bayes-Bayanen, the variational atom, and the Bayesian sharpness-aware minimization. Let's jump right in. What is it that we solve? What is the Bayesian learning problem mathematically? We start with a loss function on some parameter space. The data in the parameterized model are baked into this loss function. And we try to find a distribution Q which minimizes this objective functional. The objective is balancing two parts which are antagonistic to one another in a sense, and one can see this as an implementation of the exploration-exploitation trade-off. So the expectation term is pulling to minimize the expected loss, and if it were only up to this guy, the distribution Q would find a local or a global minimum and exploit that region by concentrating all of its mass there, like a Dirac delta at a minimum. But then we wouldn't get a new problem. This is balanced by the entropy term, which prefers distributions that are spread out and would like to explore the parameter space. So, the loss can be a complicated function of the parameters, highly non-convex. But now, in the Bayesian setting, at the cost of going infinite dimensional, the expectation term is linear in Q, and the negative entropy is strictly convex. So if we were searching for a posterior Q among all probability distributions, then there's a unique solution called the Gibbs or the Boltzmann distribution, proportional to e to the minus L of theta. But if L is complicated, this is equivalently complicated, and we instead search for a candidate Q in a restricted family, a finite dimensional statistical manifold Q. In BLR, this Q is chosen as an exponential family, and in our work, the Lie-Group BLR, we impose a different structure on Q. Khan and Ru take their candidate posteriors as members of an exponential family, which are of this form for some sufficient statistic t. For example, in the one-variable Gaussian case, t of theta is two-dimensional, theta squared, and each natural parameter lambda gives a new distribution. Updating the lambda updates the distributions, and BLR is a natural gradient descent on the lambda, so preconditioning with the Fisher information matrix turns this gradient into a gradient with respect to the Fisher metric, which is a Riemannian metric that exists naturally on Q, and the Fisher metric has many favorable properties. For example, it is also the second derivative of our objective functional, among others. I've already extolled the virtues of BLR, but there are certain issues. Let me list them. And the first one is not really an issue, but it is what it is. The update is designed only for exponential families. There's nothing wrong with that. There are a lot of exponential families which we use and love, but I'm just stating a restriction. It can feel claustrophobic. Secondly, and this is more serious, the update acts as if the lambdas are lying in the whole vector space. However, not all lambdas are allowed. Going back to the Gaussian example with theta squared, and lambda 1, lambda 2 here, one would need lambda 2 to be positive for this to be normalizable. But the update could easily overshoot such a constraint and would need to be projected back. That's what it's done, but the update is not only given by this formula. Thirdly, there is no overarching way of efficiently calculating this gradient across all exponential families. This can be done in certain families, such as Gaussians and others, but special tricks need to be found in each case, which may not be there. Our setup instead is as follows. Take a Lie group G acting on the parameters, which then also act on distributions on the parameters by push forwards. Pick a base distribution Q0 and push it around with the action of the group. We take the orbit of Q0 to be our family, and thus every element G in the group gives a distribution Q sub G in the family. For example, take the real additive group and let it act on itself, so the parameters are also real numbers. Then it also acts on distributions on the reals by translations. So Q0 of theta goes to Q0 of theta minus G. This is the push forward action. And our family is the set of all translates of a chosen Q0. Or if the parameters are on the positive reals, the multiplicative group acting on itself would stretch or squeeze the distribution and suppress it or amplify it, since it still needs to integrate to 1. Or it can be a combination of the both with affine group. Note here that if we take Q0 to be the unit normal distribution, then the action of the affine group would give all Gaussians. So the Gaussians are also included in this setup. A quick recap of Lie groups. A group is a set with a binary operation, meaning you can multiply elements in it, and it satisfies certain axioms such as identity, inverses, and associativity. A Lie group is a differentiable manifold on top of that. One important feature of Lie groups is the existence of the exponential map, which wraps the tangent space on the group. It works for tangent vectors of all sizes, so it can function as a global retraction. Using it, we can define paths xtx on G for any tangent vector x, such that the derivative of this path at the identity is the vector x. And this path can be carried to any other group element G by multiplying the whole path by G. So using multiplication, the tangent directions at any element can be parameterized by the tangents at identity. What I'm saying is a Lie group is a very homogeneous object. Classically, gradient descent calculates, at any point, the derivative of the loss at that point and moves in that direction until it reaches a point of low loss. In learning a distribution, one updates the whole distribution until it settles in a region of low loss. But now, since group elements parameterize distributions, it is enough to update the group elements, and then we can use all the tools that Lie groups have to offer, such as group multiplication and the exponential map. Here, y is the direction of fastest ascent, so that minus y is the direction of fastest descent, of the objective functional e with respect to the Fisher metric. And exp minus alpha y is an element of the group near identity, near identity for small alpha. And multiplying the group element with G gives us another group element near G with a little step taken in the direction of minus y. So we always get a group element which always corresponds to a distribution Q sub G in our family. With the Lie-Group BLR update defined as such, we can solve the aforementioned issues with BLR. Firstly, this family Q does not need to be an exponential family. One can choose the base distribution Q0 freely and then consider its orbit. Secondly, the family is closed under the updates by design. The closure property of the group under multiplication saves us. And the third point is the most important one. It turns out the group setting is the correct framework to consider the so-called reparameterization trick. Allow me to get into the weeds a little bit. In calculating the gradient, one needs to calculate the derivative of an expectation with respect to the parameter of the distribution. Using the definition of Q sub G and making a change of variables, theta goes to G dot theta, we can push the G dependence solely into L. And then, by chain rule, we get the expectation of the pointwise gradient of L. If L is a loss coming from a neural network, this can be calculated easily by backpropagation, and the expectation can be estimated by MC sampling from the distribution. The problem of taking derivative of an expectation is a common problem, especially in Bayesian variational inference, and this method is called pathwise gradient estimators. The important point here is that in the group framework, the paths are always there, and we can calculate the gradient in the of the expectation for all families of distributions parameterized by Lie groups seamlessly. We also have two bonus features. One is that the Fisher metric at Q sub g is being pulled to a bilinear form on the tangent space of the group at identity in order to calculate the y. But one does not need to calculate the Fisher over and over throughout the learning process. It is independent of g, since the Fisher is invariant under reparameterizations. So it can be calculated once and for all. And we also expressed the updates using only tangent vectors y at identity. But since all these tangents lie in the same vector space, we can accumulate y's from previous updates, hence implement things like momentum. This can also be done in standard gradient descent, but note that for gradient descent in a generic manifold, all the tangent vectors along the learning path would lie in distinct vector spaces, and it wouldn't make sense to add them. Here, the homogeneity of the group is a beautiful feature that allows for a momentum implementation. Let's move away from the abstraction and specialize the learning rule to certain groups. For the additive group on the space of parameters, the update rule looks like this. Notice that this is very similar to the gradient descent. In fact, if Q0 is very close to the Dirac delta at 0, then Q sub g is very close to the Dirac delta at g, and then this update rule would be effectively gradient descent. However, if there is some width to Q0, then the updates are calculated instead by averaging the gradient of L at certain sampled points near G. Injecting this sort of noise inside of grad L had been thought of before heuristically, and it has been shown to improve performance. For the multiplicative and affine groups, however, we get novel update rules. They are also simple to implement. And note that in all of them, the derivative is sitting on top of the L and inside of the expectation. We showed that all of these update rules here can learn the standard benchmark datasets, but they do learn differently. For example, consider the multiplicative group. For this, let's take our cue from biology, where there are distinct excitatory and inhibitory neurons. So the signs of the weights coming from such a neuron would be fixed, and only the magnitudes of the weights would be the variable parameters, which are positive. In such a fully connected neural network, we teach using the multiplicative Lie-Group BLR and look at the weights going to a single node in the first hidden layer. The weights have the same shape as the input and can be seen as a filter detecting a certain feature in this horse picture. It turns out the multiplicative group learns sparse and localized filters. Let's compare it with the additive group rule, which is similar to SGD. They both learn comparably, with the multiplicative group showing better calibration results. However, most shockingly, their learning behaviors are very different. So these are the most activated filters by the top left data. For the additive group, the information is there because it learns, but it's much more diffused. For the multiplicative group, the filters are very sharply localized. In fact, for CIFAR, I could say to you the vertical red filter that is in the center, and you would be able to point to the one that I'm describing, this one. Whereas it would be much harder to describe a filter on the left-hand side with reasonably concise human sentences. Now let's recap and also mention some of the limitations of our work. The Bayesian Learning Rule is a promising and fertile setting for the understanding of learning algorithms. BLR specialized to many existing algorithms and also gave rise to many a new successful algorithm. However, there are certain issues with BLR. And by its structure, the group framework solves these issues. And there are also some limitations to this work. Given an arbitrary Lie group, there is no guarantee for whether the model will learn with this update rule. It would have to be tested experimentally. And even if it learns, its behavior may be well worth studying, as we saw in the multiplicative versus additive cases. There may also be implementation problems. For example, if our group requires us to take the exponential of a million by million matrices, then we would need to approximate, and the effect of such an approximation on learning would have to be investigated. And that's all from me. Thank you very much for listening.